Today we're going to talk about the hypergeometric distribution. So when we were talking about the binomial distribution, it was really important that when we chose out our sample, we were choosing one and then we were replacing it back into the population that we were choosing from. What that did for us was it made it so that the probability of success and the probability of failure would stay constant from one trial to the next for our sample. Now, in a hypergeometric distribution, we don't have to replace. So what we can do for a hypergeometric distribution is we can select one from the sample and leave it out, and then select another and leave it out, and select another and leave it out. And in doing so, we can account for the potentially slightly fluctuating probabilities of successes and failures. So let's take a look at what this hypergeometric distribution looks like and a couple properties of it. When we're looking at the probability distribution of a hypergeometric random variable x, with the number of successes in a random sample size of n selected from n items, of which k are labeled successes and n minus k are labeled failures. So x is the number of successes that we're looking for. So I have an h for hypergeometric, and then I'm going to be looking at my x value, which is the number of successes that I'm looking for, where I have a total of n items in my population that I'm choosing my sample from. I'm taking a sample of size n, and k of the items in my entire population are success items. So the way I do this is I'm doing this like a general probability idea. So I'm going to be choosing for my denominator the total possible ways that I can choose a sample size of lowercase n from a population size of capital N. So that's all the possible ways that I can choose this sample. So that's my denominator. My numerator is looking at taking the k items that are labeled successes in my population and saying, well, how many ways can I choose x successes from the total number of successes I have available to me? And then, since it's independent with the idea of selecting failures, I have n minus k failures. Everything that's not a success is a failure. And I'm looking at how can I choose the remaining parts of my sample size lowercase n as failures when I've chosen x of them as successes. And I'm multiplying those two together because the probability, the number of ways for each of those is the product of the two, since they both can't happen at the same time. And so that gives me the total number of ways to select x successes and n minus x failures from my population of size capital N with k total successes available to me. Now, the range that they give here, this is all based on these three binomial coefficients that I have here. So I have k choose x, I have capital N minus k choose lowercase n minus x, and capital N choose lowercase n. So these maxes and mins that are here bounding the x variable are all based on keeping these binomial coefficients so that I don't have negative numbers involved, and so the number that's in the upper position that I'm choosing from is always greater than or equal to the number in the bottom position of items that I am choosing from that population. So we can use this equation now to help us solve problems. So let's take a look at an example where I have 40 components in a lot, and say 3 of them are defective. Now, I'm going to have a process where I'm going to sample 5 components from that lot, and if I find one defective, I'm going to say the whole lot is bad. So I'm going to see it as a success to find a defective component. So I can use my hypergeometric distribution to find the probability of finding exactly one defective component. So if I fill in my values here, x is the number that I'm curious about finding, so that's 1. Capital N is my population, so in this case I have 40 components that I'm choosing my sample from. Lowercase n is the size of my sample, so I'm choosing 5 components. And k is the number of successes that are available to me in that population. So there are 3 defective components there, and that's what my success is. So I'm going to just plug these numbers in. So I'll have my k value, 3, choose my x value of 1. So I have 3, choose 1. And then capital N, so 40, minus my k value of 3, which gives me my 37 non-defective components. And then my sample size of 5 minus my 1 defective, so the 4 non-defective components I'm trying to choose. And then I'm going to divide that by my total ways to take samples of 5, so my 40, my population of 40, choosing my 5 components. So from this, we can plug this into a calculator, or we could simplify that second binomial coefficient in my numerator really quick. So we have 3, choose 1. 40 minus 3 is 37. 5 minus 1 is choosing 4. And then our denominator is 40, choose 5. And we can use a calculator from here. I wouldn't recommend really trying to do this without a calculator. And we find that this is about 0.3011. So what this is telling us is about 30% of the time I'm going to find exactly one defective component if there are 3 defective components in my 40 component population. And now I also have the mean and the variance of the hypergeometric distribution. For finding the mean, I'm going to take my lowercase n value, multiply it by my k value, and divide it by my capital N value. And for my variance, I have to do a little bit more. So I'm going to take my capital N value, subtract lowercase n from it, divide that by the difference of capital N and 1, and then with that quotient, I'm going to multiply it by lowercase n, and then finally by k divided by n, capital N, times the quantity 1 minus k divided by capital N. So my variance is more involved. My mean is fairly straightforward. It should be noted that neither one of these depends on my x value, and that shouldn't be that it depends on my x value at all. So that's those formulas that, again, you can use these. Generally, you'll be able to just plug and chug. So I could find my mean and my variance of the previous problem that I did just by plugging in 40 for all of the capital N's, 5 for all of the lowercase n's, and 3 for all of the k values, and then using a calculator to do all of the subtraction, multiplying, and dividing involved.